All right, students, welcome back to yet another lecture for TAN 210. We're going to keep moving along with these internal forces and start looking at a little different way of evaluating what's going on in our members of interest. So last time we did a bunch of examples where we had different setups and sectioned different beams essentially in different places, and based on the external loads and the constraints identified what the internal forces were in terms of normal shear and bending moments. And we can do this for any point in a structure that we're looking at. So you see I've drawn one here where we have a bunch of different points, and I could section it here at A, B, C, and so on to understand what the loading conditions are. And so let's take a look at how, for example, the shear forces, the internal shear forces change as we look along the length of the beam, for example. So I think I have that set up here, right? So what I've done is just now drawn a free body diagram of our member here with our external load P. And let's go ahead and now apply the forces that we have. So we have a force P at D, and then we have the supports HY, AY, and AX. And we can see hopefully from inspection that we know AX is going to be 0 because there are no other forces in the X direction. And then if we did sum of forces Y in the moments, and in this case we will assume that this is L over 2, and this distance is also L over 2, so P is right in the middle. And just using equilibrium, we can see that AY will equal HY, which will just equal 1/2 P, right? All right, so with that information, let's go ahead and section this thing. First, let's start with B, right? And I'll draw that free body diagram. It's for a section at B. Here's our coordinate system that we'll use. And so if I took that section, right, I of course would just have the AY on the left, just like we've done before, normal force, shear, using the positive convention. And I can see right away that the sum of forces in the Y direction will tell me that shear will be equal to AY. Now let's do this again, and let's go ahead and section it at C. And the question I would pose is, do we expect anything to change, right? Do we think that the forces, the shear force at B will be different from that at C, or C will be different from B? Well, let's see what the answer is if it's not clear to you. If I now section it at C, right? So let me go ahead and draw those sections. So here's the section at B, now I'm sectioned it at C. And hopefully what you can see is that you actually end up having the exact same free body diagram, right? It's a little longer, but in terms of the actual forces or loads that are happening, we can see that once again, if we do sum of forces in the Y direction, that now shear is still just equal to AY, which means that the shear between B and C are exactly the same. So shear is not changing. Now what happens if we move over to D? So let's make the section at D. And now D will go ahead and include that load, the point load. So a little bit longer again. And we have AY, HY, whoops. So we'll put P here, normal, oops, this is not positive shear. Shear positive will be pointing down. And now again we have the moment. And now if we write our equation of equilibrium, we can see that the sum of forces in the Y direction are such that we have AY up minus V minus P equals 0. And so now shear is actually changed, right? It's AY minus P, so some value less than that. And then finally, let's do one more. Let's go ahead and set up for what happens at E. if we go on the other side. So if we go ahead and draw this next section, what do you think is going to happen? So again, we'll go a little bit longer now. Apply all of our forces, AY. P now is a little bit scooched over. So now we're at E. And we'll normal, shear, in a moment. And now for this one, we'll solve our equations, sum of forces Y. And what do you see? Essentially, hopefully you can see that these two diagrams, this one here and this one here, are exactly the same. And so there's not going to be any difference in the equation that we have. AY comes up, minus B minus P again. And so now shear is now again the same, right? So, and this would be the case for E, F, and G, right? Nothing's going to change until I get all the way over to HY. So let's go ahead and plot this. Now, see if I can get this to work. So this is what we know, right? And what we're going to do is actually plot what happens to shear as a function of the length of the beam, right? And we can do this a couple of different ways. But in order to start plotting these, and this is now the beginning of the title right here, shear bending diagrams, right? So we can plot these, and the way you start to set these up is essentially we see that we're going to have one set of shear forces basically at every point where we have loads, right? So let me just do this and hopefully that'll become clearer. I set this up before using this other one. All right. So what we can do is draw some lines. We'll draw a line, vertical lines, everywhere we have changes in our loading conditions. So at point D, we're going to have a line here, and at point H, we're going to have a line right here. And what I'm going to start doing is actually plotting, right, what the shear is. And now based on the equations on the left-hand side, we know that basically between right after point A, between A and point D, we have the exact same equation for shear, right? So in between here, for example, we know that between here and here, the shear is just equal to AY, some constant. And we know that between here and here, shear is equal to AY minus P. So we can actually, I don't know why it doesn't like my iPad today. I'm going to draw an x-axis which represents the location along the beam. And now I'm going to actually plot on the y-axis the shear at any point, right? So we'll plot shear, our V, basically, right? And so here, at point AY, we know that the shear is equal to AY. It's going to pop up here, and its value, AY, we've already established is 1/2 P. And that's going to be true until we get to this point. And at this point, we have a big discontinuity. And what happens? Shear now is equal to AY minus P, right? So AY on the left-hand side, if I solve this, right, I know this is 1/2 P minus P, so shear is actually negative. And so I can draw that discontinuity drop on the right here, like so. And then after that, this is going to be the case for E, F, and G, right? And so this is now, right, our shear diagram for this beam. And so the whole idea now is that you don't have to make a bunch of these different sections. The first thing you need to do is figure out, where do I expect the shear to change? And the shear is going to change anytime your loads change, right? wanting to, can get it to work over here, but not over here. Anyway, so the shear is going to change every time we have a change in our external load. So AY popped in, and so now shear moved up. Once we have P, then we get this change here and here. And so that's sort of letting you know that you actually are going to have kind of like two sections, like section 1 here and a section 2. And all you have to do then is make sort of your virtual cuts. You have to do one here and one here, right? So we could have just used section B and section E, F, or G to set this up. So the take home here is that the shear is going to change when the loads change. Okay, so what's next? What else is happening? We know that also something should probably be happening with the moment, right? So let's take a look at those. I'm going to just leave this over here on the side. Hopefully this comes through clear on your screens. So let's take a look at the moments. And we know now that we've identified that we have these two sections, right? We might expect that the moments will also change, right, relative to the shear values. And so what we can do, whoops, scooched ahead a little too fast, is go ahead and look at this first free body diagram, and this is for section 1, basically for the distance between A, Y, and P, or A and D, if you're still looking at those letters. And now we're going to just have a variable x that represents wherever our random cut is, right? Again, hopefully from up above, you'll see that you'll get the exact same free body diagram, and you can just include a variable x. And now if we write out our sum of moments equation, we know that the sum of moments about A, for example, is going to be the m from the internal load minus v times the distance x, right? Again, x is just that distance to wherever you make the random cut, and that must equal 0. And m is equal to vx. We know shear here is equal to 1/2 p, right? That's already been solved for above. So this is only the shear between 0 and L over 2, right? So if this is the case, then the moment now is 1/2 p times x. And the important thing here to notice is that x is our variable and the moment is a function of x. Right? What does that mean? It means it's not a constant anymore. It means for whatever x is, that the moment, the internal moment, is going to change. Now let's look at what happens on the other side of the beam, right? So once we now start to include p, in other words, for section 2, right, that we've identified over here. And so I've already set up that free body diagram. So the free body diagram, right, is just a section cut like the one I'm drawing on the right with that squiggly line, where we go past and into section 2. And now this is valid for what's happening for x greater than L over 2. So we can write our equation of equilibrium for moments. And we see that the sum of moments about A are now going to be a little bit more complicated. M positive, V, right, minus V times X. Again, X is just our distance to the cut, minus P times, now the moment arm for P is fixed, right? It's just L over 2 now, equals 0. I'm going to scooch this over. Clean this up a little bit. So does everybody see that here P's moment arm is a constant, right? P, based on our given problem, has a moment arm of L over 2 equals 0. And now we can solve this for M, bring everything to the other side, Vx plus 1/2 PL. Again, this time we know that shear for the right-hand side, if we look on the right diagram, we know that the shear is negative, right? It's negative 1/2 P. So we've already solved for this up above. So you have to plug in the shear for that section that you're analyzing. So, whoops. So m is therefore equal to negative p over 2, still a function of x, plus 1/2 pl. And so essentially you now have these two equations, right, that tell you what's going on in terms of the moment. So let's think about those and draw them in here. So I'm going to extend my lines. So I have a shear diagram, or sorry, a moment diagram as well. And I'll again just draw an x-axis that represents my location along the beam, and how this is going to be for the moment. So you can do it numerically, or if you think about this, right, on the left-hand side here, for section 1, we see that m is just 1/2 p times x, which is just a function of a line, right? So we can kind of start to go ahead and solve some of these. For example, when x equals 0, to be super clear, we're going to use that top equation. Let's call that equation 1. So from 1, we know that at x equals 0, the moment should be 0. And at x equals L over 2, also from 1, we can see that it's going to be 1/2 p times L over 2. So therefore, it's going to be PL over 4. I'll get the exact same thing if I use equation 2. So same. So this is from 1. From 2, I can see that I would get minus P over 2 times L over 2 plus PL over 2. So this is now going to be minus PL over 4 plus 2PL over 4 equals PL over 4. So hopefully I've proven that math to you. So in terms of the moment, what it means is that I can actually start here and plot a 0, right, for x equals 0. And I know I'm going to go up some PL over 4. And again, we know this is going to be the case, right, that this is going to be a line because we see that the function is a linear function. And the same is going to be true here, right? We also have a line, right? This is like a y equals mx plus b situation where this is our m. This is like your b, the constant. And so for m, what's going to happen at the end? What if x equals L? We can plug that in, again, from 2, and see that minus p over 2L plus 1 PL over 2 is equal to 0. And so now on the right-hand side, we know this is going to come down to 0. And hopefully that makes sense, right? We have a negative slope. This is coming down. And what we can see are a couple of interesting relationships that start to develop. When shear is positive, we have a positive slope for the moment. When shear is negative, we have a negative slope for the moment, right? And we'll talk about those more formally in a little bit, but these relationships actually do exist analytically as well. So that's kind of our first simplest example, and what I'll do next is just post two more examples that get more and more complicated.